Hello everyone, this is Greg from ChemCore. In this video, we're going to be going through the worksheet on the deuterium and tritium topic. If you haven't seen the topic video for this yet, it's linked in the description below. I highly suggest to watch it. It's literally just a couple of minutes. And in this video, it's kind of like a little tidbit. Not all courses ever really kind of focus on deuterium and tritium much. It's kind of like just like a little like note early in the course. I do kind of like to make a video about it, kind of to explain why it's useful and what it really is, because if we really clarify it, it's not going to be something that bothers you a lot. And so this worksheet is kind of like a small worksheet that's just going to kind of maybe ask you some questions on the ideas that were presented in the video. And what I want you to remember kind of for Orgo, what you would actually use deuterium and tritium for is kind of a labeling a reaction. In some ways, like you may learn a bunch of reactions and in the future you might ask yourself, okay, but how do we know that it like happens, right? It's not like we can just grab a microscope and just look at molecules move around. It doesn't work that way. So how do we know that a reaction like an acid-base reaction works the way it does? How do we know that this transfers a proton to this? And the answer is radio labeling. In other words, we can use an isotope of the atom in question. And so using an isotope can kind of release an image, or we can kind of like spot it, usually with colors, and we can actually see, okay, before and after. And if we know before and we know after, well, we know what really happened. We actually can do the same with carbon. So carbon-14 is a radioisotope of carbon, right? Carbon is usually has a molecular weight of 12. If we add 2 neutrons, it becomes 14, and we can actually label carbon moving from a molecule to a molecule. And so in the future, in the next couple chapters, when you learn certain reactions that has some movement of carbon, you'll realize, okay, this is how we figured it out. And so I think it would be nice to just kind of go through the questions answer choice by answer choice and kind of either prove them or disprove them and just talk about them. There's not going to be much kind of drawing that we will be doing in this worksheet. So the first question is asking, why did chemists in the early 20th century use deuterium and tritium in reactions? Answer choice A says to replace hydrogen because it was too reactive. That even if even if that is maybe the case, in Orgo we don't consider that radioisotopes can have a difference in reactivity. Yes, they can be a little unstable, but in general the properties when we talk about organic chemical reactions don't change. Not just hydrogen, but also carbon and oxygen and any other atom that we consider a lot in organic chemistry. That's why we never really like talk about isotopes that much. It just, we consider the reactivity to be completely the same in regard to organic chemical reactions. And so we can kind of eliminate that. B says to image and track the movement of hydrogen atoms in reaction. That's literally the point of deuterium and tritium, right? That's why we use them, because they're radioisotopes. We can kind of see them and track what happens, where they were before, where they are after. And so this is probably going to be our answer. Let's go through the rest. Because deuterium and tritium are more stable than hydrogen. Well, actually, no. They're not more stable than hydrogen. You have to consider that if you look at the periodic table, you'll see a certain molecular weight. Now, if you remember from general chemistry, the way we get this number, and it's usually a decimal, is the weighted average of all the isotopes in kind of a natural solution. And so what you have to realize is there's a reason why hydrogen on the periodic table is closest to 1. Because most of the hydrogen that exists around you exists as, regular hydrogen. Naturally, that must mean deuterium and tritium are unstable. In general, radioisotopes, although in organic chemistry, we don't consider that they have different reactivity, they are, in general, more unstable. They can go through decay, so they can lose those extra particles that they might have, whether they're neutrons or electrons or so on and so forth. You might remember this as decay. In general, they're known, all radioisotopes, not just deuterium and tritium, are known to be less stable than their than their regular atom. And D says to speed up the reaction process. If the reaction is the same, how would it speed it up? That's completely not true. Deuterium and tritium and other radioisotopes have no relation to the energy of activation. And so our answer is going to be B. Question 2 is asking, what is the primary structural difference between deuterium and tritium? What we have to know is that dew and tri come from the molecular weight. What you have to know is that dew or deuterium and tritium come from the atomic mass of the atom. And so where does dew come from? Well, remember that the only thing that kind of is important for atomic mass is protons and neutrons, because they both weigh 1 atomic mass unit. If you're unfamiliar with this, go to the beginning Unit 1, right? One of the first videos I made was on atomic structure. It was a quick rundown that you should be familiar with going into organic chemistry. You should remember that, well, to get DO, if all hydrogens, and deuterium and tritium, all have one proton, where do we get 2 from? Well, that means that deuterium must have 1 extra neutron, and tritium must have 2 neutrons to make it DO 2 and 3, right? And so the answer that best fits that is C. Question 3 asks, how should you treat D or T when they appear in chemical reaction problems? Remember, D, or deuterium, and T, and tritium, according to organic chemistry, react the same exact way and act the same exact way as hydrogen would. Whether it's an acid-base reaction or any of the reactions that we might learn in the future, they're going to act the same exact way. That's kind of the point. We want to see how hydrogen and what is really happening to hydrogen. That's why we use deuterium and tritium. And so the best answer choice that fits that is C, just like hydrogen, only with a different label. That's literally it. Question 4, what real-world application most likely still uses isotopes like deuterium or tritium? And so this is kind of maybe using your outside knowledge. Organic farming, why would that require a radioisotope? That doesn't really make sense. Space travel, you might be kind of tempted to put space travel. I can kind of see where you're coming from. If you're thinking like, okay, physics or something like that. In general, when we're talking about engineering, the amount of hydrogen or deuterium or tritium, it doesn't really matter, right? Like if they all act the same way, why would it matter whether you're focusing on hydrogen, deuterium, or tritium, unless you're trying to label something, right? And so space travel is probably not accurate. Nuclear medicine, answer choice C, is kind of interesting. If you're not sure what nuclear medicine is a field in which we kind of use radioisotopes to track absorption or a secretion of certain bodily elements, right? Whether it's the blood or oxygen or sugar or, some other things, hormones. And so nuclear medicine, we might have to use deuterium and tritium if we're trying to track how hydrogen or hydrogen isotopes or compounds containing hydrogen can move through the body. And so that's probably something that we'll choose. In metallurgy, if I'm reading metallurgy, I don't even know really what is metallurgy. I guess it's working with metal, which wouldn't really have anything to do with hydrogen or covalent compounds in general. And so I'm very doubtful that it would matter if we're making metal or using metal. How would deuterium and tritium be important, right? And so the most likely answer choice for us is C, nuclear medicine. Answer choice 5, at this point, we're kind of getting into reactions using deuterium and tritium, and these are going to be good practice for you to realize, okay, I just treat it just like hydrogen. The product of this reaction, CH3CH2 lithium plus D2O, is, well, what is D? It's just treat it like H. Pretend it's H, and then figure out where it went. What I like to do is that, okay, if lithium is here, that means it must have a positive charge, which means that over here, on the carbon, we must have this lone pair and that negative charge. And what really happens is that, okay, if it has that negative charge, it probably is going to grab one of these deuteriums or hydrogens, and that bond between the hydrogen and oxygen is just going to break, and the lone pair is going to go to the oxygen. And what we'll end up forming is CH3, CH2D, and then plus, we're going to have that negative oxygen. But because it's negative, we're going to have that lithium kind of hanging around. That doesn't just disappear. And I made a mistake. It shouldn't be H, it should be D, right? And so the answer choice that best fits this, product is D. In question 6, which reaction will yield CH3CH2D? And so this is actually kind of a repetition question. In B, it's kind of asking the exact same question as we are asked in 5, kind of the going back. And so if you can realize that, okay, none of these will kind of form what we formed before, and we'll have an O here, no reaction will kind of happen here, and no reaction will happen in A. And so B best fits that, best fits the reaction. In question 7, we're trying to figure out a sequence that will best use to prepare CH3C triple bonded C and D. And so what we realize is, okay, all of these answer choices are kind of starting from this triple bond. When we realize we have to kind of, in each of these, we have to replace or somehow maybe get rid of and then replace the H with the deuterium. And so how can we do that? Remember, to get rid of an H, the best way to do that is let's just use a base, right? If we use a base, we can kind of take off that H, and we're left with a carbon, right, that really wants something because it ends up as either a carbon anion, probably a carbon anion, or a carbocation. In this case, since it's an acid-base reaction, it's going to act as carb anion. And so what we really have to realize, okay, D doesn't work because this isn't a base. It's not going to abstract the hydrogen. C, I guess, could work B, I guess, also could work. It's also a base. And then A, I guess, also works as well. And so all of these reactions will have a final step or a second step of using D2O. And one of these carbons in each of these reactions is going to end up grabbing the D and creating our product. So if all of these technically work, which answer choice do we use? The keyword is which sequence is the best, all right? And so this gets into idea of, which ones are your better bases, which ones are your worst bases, better acids, worst acids. And so this is really using the concepts that we talked about in the last video. If we want the best reaction possible, we want to abstract this hydrogen, the one we began with, as as efficiently as possible. We want to get 100% of it off. And so the best way to do that is to use the strongest base. And so one thing that you'll realize is that NaH, out of all of these three options, is absolutely the best base possible. Think about it. It's a hydrogen that is negatively charged. It definitely doesn't want to be negatively charged. First of all, it's a diatomic gas. Remember Brinkelhoff, it can exist. It wants to exist as H2. And so if it exists alone, it definitely doesn't like that, right? Out of all of these options, A will probably abstract that hydrogen as fast as possible because it wants that hydrogen. It's really jealous for it. And so A is probably going to be the best reaction to prepare this product. Question 8, the final question, is asking if the following compound was treated with excess NaOH followed by an excess of D2O, what would be the structure of the new product form? And so let's redraw this kind of structure. We have that triple bond and then an OH coming off here. And if we treat with NaOH, we should I like to mention for myself, okay, this O must have 3 lone pairs and a negative charge, and that sodium must have a positive charge. It's not that important. It's a spectator ion. It's not really going to act in our reaction. But what we should note is that OH, this negative charge OH, is a really good base. And so it kind of wants to steal a hydrogen. It wants to become H2O. And so the best acidic hydrogen that I can see here is the hydrogen that is attached to the oxygen. Is it possible, technically, that we can abstract instead one of the hydrogens hanging off here? Maybe, but it's so much less acidic than that hydrogen attached to that oxygen that if we were to abstract the hydrogen, it will probably come off that oxygen. And so what's going to happen is that we're going to reach over, we're going to attack this hydrogen, and actually it'd be useful for me to maybe show that bond between that oxygen and hydrogen. And once it steals this hydrogen, these two electrons will go over to that oxygen and we form an intermediate that kind of looks like this, right? Pretty interesting. We're going to have 3 lone pairs around this oxygen and a negative formal charge. And we kind of end up with a side product that we just formed. We just formed H2O, right? And so this sodium that we had before doesn't really go anywhere. It's still over here, right? And we're not really done with here. We said that we also had an excess of D2O. And I'm going to draw the structure out. Remember, it's going to look exactly like H2O except D instead of H. And so since it has a negative charge, it kind of wants to steal another D back or another hydrogen. And so what's going to happen is that this lone pair is going to attack this D. And then this bond will kind of pop off and go to the oxygen. And then we end up with our final product. Let me just zoom down and scroll down a little bit. We end up with our final product in which we have this OD, right? And I know my face is kind of blocking. Let me move down a little bit more. Now we have this OD and we just have 2 lone pairs over here. And we have that side product with the one that we stole the D from. We have this negative charge and we have that sodium from before. And usually you don't even have to show the lone pairs or the formal charges. I'm just clarifying. I don't want you guys to think like, okay, where did the sodium go? It's still here, right? Nothing disappears. It's just not really doing anything, right? It's just hanging around the thing that's oppositely charged. And so our main product is going to be here. We don't really care. I guess some professors will ask you to draw this side product. I remember my professor didn't really care because of the fact that it's not organic, right? We're only really asked, if it's organic chemistry, we only care about organic products. And so this is the product that we're really looking for, right? This is the main product. This question concludes the worksheet on deuterium and tritium. This is kind of an easy concept. It's not really much. If you're familiar with especially Bronsted-Lowry reactions, because remember Bronsted-Lowry reactions were transferring hydrogens. If deuterium and tritium work the same way, understanding Bronsted-Lowry reactions are kind of pretending that the D is actually an H or the T is actually an H. All your reactions work the same way. It's kind of just important to understand why we use deuterium and tritium. If you're unfamiliar or you want to review these topics, go back to the topic video that's linked in the description below. And worksheets and answer keys are always available in the description. And I'll see you guys in the next video.